I'm Gary, NA6O. Welcome to Antennas for the Great Unwashed. Anybody who's not an engineer is going to benefit from our little talk today. So, antennas are very, very important to amateur radio. Obviously, you can't communicate at all without them. But there's a lot of mysteries, a lot of myths, and all kinds of, odd stories that attend antennas. And you don't actually have to have a deep theoretical knowledge to understand how things work on a practical, intuitive level. So that's what I want to talk about today, is kind of an approach where you can look at an antenna and generally understand how it works, have a feel for maybe, is this antenna suited to what I'm trying to accomplish, and things like that. So first, a couple things. Everybody should have this. This is the ARRL Antenna Handbook. It's been in publication for many, many years. Excellent authorship. I know a lot of the guys who write in this book. I've even contributed to it. And there's no reason to Google things up. Don't ask someone who probably knows less about antennas than you do. Try looking in this book. This will probably give you some authoritative answers. Another thing I want to say is that when it comes to antennas, I'm going to use a quote from a very famous antenna designer, N6BT, who said, "Everything works." So one of the things that he did is, very famously, he mounted a 100-watt light bulb on his fence, connected his coax up to his transmitter, and during a CW contest, he promptly worked all continents in a matter of a few hours. So that's with a light bulb on the fence. So if you read the reviews in EHAM and things like that, by golly, when it comes to antennas, everything works. And in a sense, it kind of comes down to that, because if you can get current into a conductor, it's probably going to radiate, and everything sort of works, more or less. But the question is it efficient? Is it effective? Is it optimum for what you're trying to accomplish? So I'm going to start off with, how the heck does an antenna radiate? All right. Before your very eyes, the great Uncle Gary shall turn this ordinary balloon into a radio antenna and transmitter system. Hard to believe? Are there doubters out here? Well, I'll show you. First, I require some electricity. There we go. What little hair I have is now standing in. All right. So I've tried to electrically charge this with ripping electrons off some poor innocent atoms and piling them on my balloon. And now, let's see. Yep, by golly, there's a little electrostatic charge in this balloon. So I have here one bucket of electrons. Well, that's kind of interesting. If I have a whole bunch of electrons in one place, what does that do? Well, it creates an electric field around it. Okay, what's a static electric field? How far does that electric field extend? It goes off to infinity. Well, that's kind of neat. So I've actually distorted the electric field of the entire universe. How often have you made an impact on the entire universe? Well, that's what this does. Now, it falls off as the inverse square. So twice as far away, it's 4 times as weak. So yeah, at a distance, it's not very strong. And also, it's just a static field. Now, we're swimming in static fields, so there's very little you can do with just a static field. But I do have a bucket of electrons here. Now, in order to make this more interesting, what I'm going to do is invest everybody here with a very sensitive, magical electric field detector. Okay, so maybe you're a hammerhead shark with a bioelectric sensor, or maybe you have very fine pieces of paper here. Anyway, but you can all detect weak electric fields. Right? So now I'm going to take this balloon, which is all charged up, and I'm going to suddenly move it towards somebody. So what happens? The field gets a little stronger out there. I move it away. The field gets a little bit weaker. Now you have a difference. Okay, you can detect a difference in the field. Now that's significant. The static field is very boring, but a sudden difference, now that's something you might be able to actually detect. Oh, by the way, how long did it take from the time I moved this balloon and distorted the electric field here? How long did it take until it reached, say, the back of the room? Well, it traveled at what? The speed of light, 300 million meters per second. Well, a better way to remember that is light travels about a foot in a nanosecond. So you're, 20 feet away. Well, it took 20 nanoseconds for that change to get to the back of the room. So this energy, this little change in electric field is propagating off in the universe at the speed of light in all directions. Now, what if I did something like this? I vibrate my little balloon. Now I'm creating an oscillating field. It's kind of interesting, an oscillating field. And at some distance, it gets closer, farther, changing at some rate. Now, what if I change that little field? I was able to shake this at 1,000,000 times per second, 1 megahertz. Okay, that's a radio frequency in the middle of the AM band. I'm able to move this 1,000,000 times per second, sending out little ripples in the electric field, heading off to infinity, getting weaker, of course, but heading off to infinity. So when I do that, everybody with an electric field detector should be able to tune themselves to 1 megahertz and detect that little electric field disturbance that's occurring. So this is a bucket of electrons I'm moving around. When I move electrons, I'm doing work to move a bunch of electrons around. That's actually considered an electric current. In fact, the measure of electric current, you have 1 coulomb of electrons, that's 6 times 10 to the 18th electrons. You move that past a point in 1 second, and that's 1 ampere. So if I had a coulomb of electrons and I moved it, past this point in 1 second, that's a 1 amp current. So I'm actually creating a small electric current. I'm changing with respect to time. So now I have we'll call it a radio frequency generator here. And because I'm distorting the local electric field, that propagates. And that really is the fundamental thing of how an antenna radiates. You have a current, it's causing electric field around that area because you're moving electrons around, and that then proceeds to radiate. Now, there's another thing that happens that's totally unexpected. Whenever you have this electric current flowing, we're moving electrons around, creating electric current, you're also creating a magnetic field. And it has exactly the same characteristics as the electric field, except it's perpendicular to it. So you wonder, why does an electric current cause a magnetic field to occur? Well, I will take a quote from the great physicist Richard Feynman. His answer to that, nobody knows. However, we have some mathematics that completely predict all of our observations. And that's things like Maxwell's equations, and all those other obscure things that everybody who's taken physics and things like that knows about. So what matters is you have to produce an electric current, preferably in a conductor. Balloons suck. But you have a current in a conductor, it'll generate an electric field and a magnetic field. You get both for the price of one. So that really is, the fundamental ground reason that an antenna radiates anything at all the magic of a simple balloon. So before we get into actually the details of antennas, I want to go over some kind of important properties, materials. We'll do some transmission lines, talk about SWR, impedance matching, some things like that. So first up, I want to talk about skin effect. So we're passing current through conductors, right? We have to know something about the conductors that we're using. So I have here 2 chunks of aluminum. They're the same size. One's a solid rod and one is a hollow tube. They're the same diameter. One's hollow, one's solid. So if I pass good old DC through both of these, through a long conductor, this big solid rod is going to have much, much lower resistance because there's just so much mass to it. No question, it has lower resistance than the hollow tube. But something completely different happens for alternating currents and especially for radio frequency currents. Whenever there's a current change going on in a conductor, it generates something called eddy currents in there. And what it ends up doing is it forces all the current to flow on the surface of the material, on the surface of the conductor. So at a radio frequency, for this aluminum, for instance, the depth of penetration is only a few thousandths of an inch. It's very, very shallow. And the higher the frequency you go, the shallower it gets. By the time you get to microwaves, it's just a vanishingly thin amount. And that's why a lot of microwave conductors are gold plated, because it's only that very, very thin top surface where all the current flows. So for radio frequency, the tube and the solid rod are basically the same. Now, there's no reason I would want to build an antenna out of solid rod. In fact, a mechanical engineer will tell you that all the strength in a tubular member is out in the outside edge anyway, and the big core is very unhelpful. It's just a lot of weight. So that's why we build our antennas out of things like tubes. When we're building, say, a Yagi or a big vertical, we want lots of strength. We use things like aluminum tubes. So aluminum and copper are very close. They work just great. Every once in a while, you see someone make an antenna or something out of steel. Now, there's a problem with steel. First of all, its resistivity is higher. So whether you're talking about a solid steel wire or hollow one, doesn't matter. Its resistivity will be, say, 10 times higher than copper. So it'll tend to be a somewhat lossy material. But it gets worse. If you're using actual normal steel, that's also a ferromagnetic material, right? A magnet will stick to it. That makes the skin effect even worse. So instead of being, say 3,000 for the penetration of your radio frequency, it might only be half a thousandth of an inch deep or something like that. So now all the current is flowing in a very, very thin sheet on your conductor. And the result is an even higher loss. Sometimes you call it AC resistance. And there's actually formulas for that. So the upshot is steel is not your friend when it comes to building antennas. Sometimes it's necessary because of strength, and then they'll use something called copper clad or copper weld wire. You may have heard of that. It'll be a steel core for strength, and then they'll electroplate a heavy coat of copper on the outside of the steel. And all the current is flowing in the copper on the outside, and the steel core is just there for strength and doesn't really, cause you any problems. So if you want to build a wire antenna, you run down Home Depot and you get the 12 gauge THHN house wiring, works fine, lasts a long time, cheap. You don't need anything exotic. You can make antennas out of very fine wire if you need to keep things invisible. The AC resistance goes up a little bit. It eventually becomes mechanically fragile, but we usually stick with, nice robust wire. It's easy to work with. So that's skin effect. The next thing I want to talk about is transmission lines. In order to get power from your transmitter up to the antenna, you need some kind of transmission line. So first, let's talk about this kind of transmission line. So this is what we call a balanced line. Sometimes it's called ladder line, window line. And this particular kind has two conductors separated by some plastic. Other kinds are made with separate conductors that may be several inches apart with typically plastic spacers in between them. It really does look like a ladder in that case. And this is what we call a balanced line. Everything about it is very symmetrical. You can't tell one side from the other. Works just fine. And these have a characteristic impedance. This one's have to be about 450 ohms. The really wide ones tend to be something like 600 ohms or so. This is what we call a balanced line, very symmetrical. Now, in contrast, more often we use a coaxial cable. So here is a gigantic model of coax. So what is coax? A coaxial cable consists of a center conductor and a shield. And everyone looks at the shield like, well, it prevents radiation from getting out of the coax, you might say, and also prevents interference from the outside from getting into the coax, and that's true. It certainly does that. So in coax, just like with the parallel transmission line, the energy is carried in, there's an electric field between the conductors on the inside here. And there's also a magnetic field circulating around the conductor. And the impedance of the coax depends on the dimensions. Basically it's the inside diameter of the shield and the outside diameter of the center conductor, as well as this dielectric material that's on the core here. And this actually is polyethylene, by golly, and most coax uses polyethylene. So another name for coax is an unbalanced transmission line. Now, what makes it unbalanced? Why is this unbalanced? Is because, well, one conductor is little and one conductor is big. Well, no, that's not what makes it unbalanced. What makes it unbalanced is skin effect, and here's why. So when I connect these two conductors, up to an antenna. I connect the center conductor to one side of my antenna and the shield to the other side of the antenna. Now, because I've told you about skin effect, the current is flowing down the inside of the coax. It's flowing on the center conductor, and it's flowing on the inside of the shield. And that's what gets the antenna. But notice the antenna is also connected to what? The outside of the shield. And guess what? The outside of the shield is also a conductor. And it's separate from the inside of the shield because skin effect. The current on the inside only penetrates so far. Current on the outside only penetrates so far. And depending on the quality of the shield, the two probably don't even meet. So what happens is the shield of your coax and the entire length of that coax becomes part of one side of your antenna. I don't think that's what I had in mind. I mean, I put my antenna up and I have two wires coming off it, one from the inside, one from the outside, and that's all I want. Now you're telling me there's another wire hooked up to my antenna. Now, wait a minute, that's going to mess things up, and it does. It changes the pattern of the antenna, noise that's conducted to the shield of the coax arrives on the antenna and then can go down the inside of the coax. That's a great way to get interference picked up, things like that. So we have to do something about that. And the answer is we use a thing called a choke. And a choke is a device that adds a high impedance to the outside of the coax. So the current is stopped cold by a choke put around it. So what does a choke look like? Well, here's one. You can make chokes all kinds of different ways. This particular one is made from some small coax that's wound around a ferrite core, a ferrite toroid. This is a very effective choke. This looks like several thousand ohms over most of the high frequency bands. So if current attempts to flow down the outside of the shield, this looks like a big inductor. It also looks like a bit of kind of a lossy inductor, and that energy is quickly dissipated in this choke. Now you can also make chokes simply by taking a bunch of coax and just winding it into a coil. Now the signal on the inside doesn't care. It's like water in a hose. It doesn't matter if you bend the hose. The signal on the inside that's totally unaffected. It's only the current on the shield that's seeing this increased impedance that prevents that energy and that current from flowing down the outside of the shield. So that's why a choke like this, sometimes also called a balun, balanced to unbalanced, we'll get into that more. Sometimes it's called a balun. That's why that's quite necessary on most all antennas that are fed by this unbalanced coax. Now, one thing I mentioned was, I said this has a characteristic impedance of 450 ohms, and the coax is typically 50 or it could be 75 ohms, something like that. Well, what's this impedance thing? Well, I whip out my ohm meter. I said, oh, okay, the guy said this is 450 ohms. I hook my ohm meter up this thing, and it's an open circuit. Well, yeah, it is. It's just two parallel wires with plastic in between. They're not connected. Yeah. There's nothing 450 ohms about this. You got to be kidding. Well, there's actually a better name for it. We call it a surge impedance. Okay, so what's a surge impedance? Well, here's how it works. What you need is a faster ohm meter. So, you look at me like I'm nuts. No, you need a faster ohm meter. Now we have them. We have fast ohm meters. So how does that work? All right, so I have a transmission line like this, and I make it tremendously long. Now, the thing about this is, okay, I have two wires that are near each other. Whenever you have two conductors that are near each other, we've been told that makes a thing called a capacitor. A capacitor is a thing where you have an electric field between two conductors, and that electric field is a place you could store energy. It doesn't dissipate any energy, but it stores it. And in order to put the energy in that electric field, you have to generate some current on the cable, and it charges the capacitors all along this cable. Now, this cable goes off for a long, long distance. You can imagine there's a lot of capacitance. It builds up over length, right? A bunch of capacitors. So if I inject current in there, I can actually watch the current charging the capacitor. Now, if you ever tried, you take a great big electrolytic capacitor, big ass thing, hook your ohm meter up to it. What you'll see for a moment, it looks like a dead short, and then the resistance goes up, and you're charging the capacitor. Well, the same thing would happen with the transmission line, but there's more. The transmission line also, because it's a long, skinny conductor, it also has inductance along its length. So a wire doesn't have to be in a coil to make an inductor. Remember, inductor stores this energy in a magnetic field. Capacitors are electric field, inductors are magnetic field. So an inductor can be formed by just a straight wire. It's about 20 nanohenries per inch, something like that, for a straight wire. So this transmission line looks like an inductor, capacitor, inductor, capacitor, inductor, capacitor, an infinite number of those things, which is really kind of an interesting network. You can build one of those. You can build a bunch of inductors, capacitors, and it'll simulate a transmission line. All right, so what happens is, if I suddenly inject current into this thing, I'll start charging capacitors. I'm also starting to charge the inductors, and they act as a kind of a delaying mechanism. And so what will happen is that current will suddenly rise up to a certain level based on what amounts to the ratio of the inductance capacitance. Actually, it's the square root of the ratio. So if I have a very, very fast ohm meter and I connect it to this, what I will see is, in this case, it'll read 450 ohms as long as that pulse is heading out down the cable. Or if it's coax, it'll read 50 ohms. So the instruments that do that are things like a thing called a time domain reflectometer. I love that name. And a TDR, as we call it, it's an oscilloscope that looks at this, and it generates a pulse, a sudden pulse of current. And you watch the magnitude of that, and you can see the voltage jump up, and in fact, it goes out and reflects on the cable and things like that. So we do indeed have very fast ohm meters, and if you hooked it up to this, it would say, oh, that's 450 ohms, by golly, but only in a dynamic sense, not in a static sense of an ohm meter. Now, if you hook your ohm meter up to this and you see a dead short, oh, you got a problem because somebody's gone out and crowbarred your transmission line. So ohm meters are valuable just for the purpose of troubleshooting. There's also another thing called velocity factor. You send something in here, some kind of a pulse. It does travel at something approaching the speed of light. The thing about speed of light is energy that's traveling in a medium, even if it's in the air, let alone in something that's plastic or something else like that, light slows down. So we have a velocity factor, we call it in coax and other transmission lines. Coax velocity factor is like 70, 80% of the speed of light, something like that. And in the open wire, stuff like this, it's something up in the 90s, pretty fast. This is also very low loss, very, very low loss. It's just these are the lowest loss transmission lines we know of. All right. Next, we're going to talk about impedance matching. All right. It's showtime. All right. I told you this is going to be old school here, folks. Yes, indeed. Remember in the 1960s, teachers standing up there with their little props and things. So here I am. Welcome to 1965 ham radio training. All right. So very important thing about anything to do with antennas is impedance matching. So long story short, you have a source over here, you have a load over here, and if the impedance matches, you get the best power transfer. All right, so very important to keep in mind, our objective is to deliver power to the antenna. Power is the thing that is used to move information. There's some great information theories that it takes a certain amount of energy to move a bit of information. So we have to deliver power to the antenna, which is then used to distort the electromagnetic field of the universe in order for us to communicate. So we have to deliver power. All right. So over here I have a source. In this case, we'll say it's a transmitter. This could be, for impedance matching, it could be AC or DC, doesn't matter. And one of the things about any source is it has what we call an internal resistance or internal impedance. If it didn't, if I put a short circuit across here, all we have is say this is a battery, there's some kind of resistance, you short circuit it. If there was no resistance, the current would go to infinity. Well, nature doesn't like infinity very much. So instead, there's some amount of resistance here that will limit the maximum amount of current. If you have a battery, for instance, a car battery, that resistance is very, very low, milliohm or something like that, and the current goes to hundreds of amps. And our transmitters, typically, it's 50 ohm, thereabouts. Then over here at the load, we have some kind of load resistance. So if you work through the math, if you feel like doing math and stuff like that and proving it, you'll find out that to get the maximum power delivered to load, the load resistance needs to match the source resistance or impedance. A good test of, why is that true? Well, you can do the math to say. The other way you can do it is say we put a short circuit out here. All right, if I put a short circuit out here, the current in this loop is going to be at its maximum. Yeah, baby, I'm ramming the current into that load out there. Well, that's fine. And my voltage, you have to look here, I have a voltmeter and an ammeter out in the load. Well, the current is very high, but now it's short circuit, so the voltage is zero. Let's see, power is the product of voltage and current. Multiply voltage times current. Well, the current's very high, but the voltage is zero. So with a short circuit, I deliver zero power. What if I go to an open circuit over here? Okay, there's an open circuit. The voltage goes way up, but the current's zero. So once again, no power. So an open or short, those are the boundary conditions. Open, short, open, short. I get zero power at either one of those. So there's somewhere in the middle, there's a happy medium where I get the maximum power at the load, and that's when the load impedance matches the source impedance. So that's our impedance matching. And we go to great lengths to make that so in our antenna systems. The next thing we're going to do, we're going to look at this in terms of radio here. This is a transmitter. This is a long transmission line going to, say, an antenna or some other kind of load. And the first thing I want to do is find out what happens along that transmission line, especially if this is not a perfect match. The best way to start this is the good old water analogy. Everybody who's learning anything about electricity, right away you start with water, right? Water pressure, water flow rate, that's voltage and current, things like that. So we're going to go with the water analogy. So say that the transmission line is a pond. The transmitter is, well, it's stones dropping into the pond. So I drop a stone in the pond, it launches a wave off across the pond. And depending on the length of the transmission line, it may take a while to get there. And say at the load over here, that's the shoreline. And the shoreline is this mushy, marshy, grassy kind of area. So I drop a stone in here, it travels over, hits this little marshy area, and it just kind of goes poof, it just kind of dissipates. What have I done? I've taken the energy of that stone dropping in the water, transferred it via a moving wave. We call that a forward power, and we've delivered it to the load, and it's been dissipated as heat over there on the shore. So that's what we call a good impedance match. So you have just a forward wave and nothing comes back. Now let's put a brick wall over here. We got the breakwater, hard concrete, something like that. Drop the stone in, the wave goes over. What does it do? It bounces off. It's not dissipated there, it simply reflects. So now we have a forward wave, and then we have a reflected wave. It comes back. Now, where does it get dissipated? Well, in the water analogy, it just kind of goes on past me, goes back the other way or something like that. In the case of a transmitter, it actually gets dissipated here in that source impedance. So clearly, a reflection like that is not necessarily something we want because we're not delivering power to the load. So another thing happens. If I start dropping stones one after the other here, one after the other, I can drop stone, 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 stone. I'll generate a nice continuous series of ripples. And if you ever had a physics class, you work with a ripple tank, that's exactly what you do. You have a ripple tank. They're really cool. So it sets up all these little ripples in the water, and they head out here. And if there's a match, all you have is these little traveling waves, little traveling waves. Little traveling waves move over and they just disappear. and that's it. Everything's happy. All the power has been transferred here there. But if there's a reflection, the wave bounces off and comes back. It may come back in the same polarity, it may be inverted polarity, it depends what's out here. And what happens is the two of them meet along the way, one going this way, one going that way. And what happens is some places they add, some places they subtract or cancel. And what you'll see is what we call standing waves. You'll see oh yeah, it's bigger here, smaller there. You'll have some kind of what we call a standing wave pattern caused by those reflections. The bigger the reflection over here, the poorer the match, the bigger the standing waves are. So exactly the same thing happens with RF. So one of the things we do is we have a thing called an SWR bridge. A reflectometer is another name for it. This is an instrument that actually is able to sense the wave that's traveling forward and reverse. And with some little math, basically like a ratio of those, it gives you an idea of what we call a standing wave ratio. But there's another way we can do this. Old school again. Back in the old days, before SWR bridges were invented, what these guys would do on their old spark transmitters in 1920 is they would actually walk along the line with a voltmeter across their big open line transmission line. And they would walk along with a voltmeter and they would slide it along their transmission line. And what they'd be doing is measuring the voltage everywhere along that line. And what would happen is, if you had a good match, the voltage would be the same everywhere. There's no standing waves. You only have the traveling waves, so it averages out. It's the same voltage everywhere. Or you could use current. If you had a clamp-on current meter, you walk along like up, the current is the same everywhere. If there's standing waves, if there's a mismatch, you'd find a place, oh, the voltage is a little lower here. Oh, it's higher here. You find a peak, you find a dip, peak, dip, and it would repeat as you go down the transmission line, kind of following the wavelength that you're dealing with, whatever the 300 divided by frequency in megahertz, that's the wavelength. So you would actually be able to measure the frequency that way. Kind of neat. You measure your wavelength, you know what your frequency is, but also you're measuring what we call the standing wave ratio. And the ratio is the peak voltage to the minimum voltage, or the peak current to the minimum current. That ratio, that is SWR. It's also equal to the ratio between that impedance and that impedance. So if this is 100 ohms, this is 50 ohms, that's a 2-to-1 SWR. And if you want sliding down to your voltmeter or your current meter, you would see a ratio of 2-to-1 from the peak and the dip. So the implication of SWR is, number one, it's a diagnostic. It tells me what my impedance match or mismatch is. I have a direct measure of it with this handy meter. And these meters, of course, normally built into our transmitters today, but you can add one on. And it gives you an indication. At the same time, you're actually measuring forward power. And it really does tell you, something about the health of your system. So we say we want a really good match in order to basically make our transmitter happy and to optimize the amount of power that's delivered. So there's another element we normally add, and that's an antenna tuner. So here at the transmitter, it's fixed at 50 ohms on most transmitters. Old tube transmitters are different. They had a network that it actually sort of included an antenna tuner built right into it, a pi network as it was called. But our modern solid state transmitters, they're sort of fixed at 50 ohms, nothing we can do about it. So we have an SWR meter. And the antenna tuner is a network of capacitors and inductors. And its job, we can also have transformers in it. Its job is, in a lossless fashion, to transform whatever impedance it sees here to fit over here. So we adjust this until our SWR meter says what we call 1-to-1, 50 to 50 ohms. We adjust that until we have an apparent match. So what's that doing? The transmitter now is going to see 50 ohms. The transmitter is able to generate its optimum amount of power, at least to this point. The antenna tuner, sometimes called a transmatch, its job is simply to transform 50 ohms to whatever's out there. So, and it does that without any loss. There's no loss in this thing. Well, practical tuners, there's some loss. it's 5%, 10%. In really bad conditions, the thing will, start smoking on you. You have a really bad mismatch out here. Some antenna tuners, you have nothing at all to it. Just you disconnect the antenna, the thing will tune right up. Yeah. So it tunes up. Yeah. Oh yeah, SWR is 1-to-1 going into that baby. There's no antenna hooked up to it. Where's the power going? Yeah, wait, you'll find out. So its job is simply to accommodate any mismatch that's out here. And at that point, all is well. So, the forward power is going this way, it continues, and it keeps on going because everything is matched on all the way out to the load. So one of the great, myths about SWR, the SWR is perfect on my antenna. In fact, the SWR is perfect on every frequency. It doesn't matter where I tune on this mystical antenna. It's something like Comet would make. Look out for Comet, folks. Avoid. Yeah, you look at Comet. Oh, yeah, I put this antenna out, give it 5 stars here. I got SWRs 1-to-1 on all bands, all frequencies, all day, all night. It's fantastic. Well, I can say it's the same thing about my dummy load. I have a 50 ohm resistor. I stick it on my transmitter. Yeah, it's 1-to-1, every band, no question about it. It also doesn't radiate anything, So something's going on with that antenna to give you a perfect match, but it doesn't say anything about the antenna's efficiency. How much of that power is actually being radiated? Dummy load, it's a perfect match, and it radiates nothing. Although you get a leakage out of your coax. There used to be a competition for the best DX, best distance worked on a dummy load. You had to run 100 watts in your dummy load. You couldn't run a long cable, that would be cheating. You had to be short cable dummy load and see how many contacts you can make on your dummy load. So you watch out for that. So that's a very important fact about antennas, and especially antenna advertising. The SWR is perfect everywhere. You have to ask why. Why is that true? Now, there actually are a couple of valid designs that basically do that. They have a penalty of actually dissipating half the power. Now, half the power isn't the end of the world. I deliver 100 watts and 50 of it is radiated and 50 of it is dissipated in the resistor, but it gives me very wide bandwidth and I don't have to fiddle with the tuner. And that was classically used for some military systems where they needed to deploy quickly on the HF bands, hurl this antenna up in the trees or whatever it was, get the dang thing on the air without worrying about, the SWR isn't perfect, it's no good. No, you didn't have to worry. So you traded off efficiency for a good match everywhere. All right, so that's pretty much what I want to say about SWR is, yeah, you want a good match to keep your transmitter happy. That's what it's for. Keep your transmitter happy and effectively transfer power from transmitter to antenna. So we typically have an ATU, and today most HF radios will have that built in. VHF radios, not so much, and you're kind of at the mercy of how well the antenna is designed and installed to give you about 50 ohms out there. All right.
Is there an advantage to have the tuner right at the
So the question is there an advantage to having antenna tuner at the antenna versus at the transmitter? Well, actually, there can be. And one of the reasons is, so we have, coax, whatever it is, some kind of transmission line running from our shack out to the antenna. And under optimum conditions, that coax or parallel transmission line, whatever it is, it will have a certain amount of loss. And loss gets worse at high frequencies, things like that. But it's pretty small in most cases, except if you're going, many hundreds of feet. So I have fairly low loss transmission line, everything's fine. But a funny thing happens. If the SWR, the mismatch is very high, very, very bad match. I mentioned that as we move along that transmission line, we see high current, low current, high current, low current. Well, what happens is you get those spots where the current is very high, and particularly on the center conductor of coax, that center conductor has some AC resistance, there's some loss. So there's actually kind of an enhancement factor of having that very high current. And at those spots, the coax will actually start to get warm. In severe cases, you can melt it. If you're running high power into a bad mismatch, you can get spots hot enough to actually melt the coax. So that's what we call I squared R loss, current squared times whatever resistance is in actually the center conductor of the coax. So there is this added loss in the transmission line from having a high SWR at the antenna. Now, if it's 2 to 1, 3 to 1, something like that, I mean, don't worry about it. That's like no concern. And the amount of extra loss is very small. There's tables in the antenna handbook that will show you what this extra loss apparently is. And it's small enough not to worry about it. But if you're operating some extreme condition and the SWR, it's a bad 10 to 1. It's not a 50 ohm antenna, it's a 500 ohm antenna, something like that. And that happens. There's reasons some may actually design it that way. Now you have to look more closely at that mismatch. And that's a case where having the antenna tuner at the antenna transforms this weird 500 ohms, whatever it is, maybe to 50. And now the coax just sees 50 ohms all the way back to the transmitter. Everything's perfect. But of course, you need the antenna tuner out in the yard or wherever it is with remote control. All right. So next up, let's talk about antennas themselves. Behold, the dipole. Excuse me while I extend my elements. All right. So this is the most important antenna to understanding everything else. So what is a dipole? The basis of a dipole is there's a feed line coming in. I want to go this way. It works a lot better this way. There's the conductors. They have the coax coming up. They got two conductors. And the standard length for a dipole is a half wavelength over its length, half wavelength. So it's a quarter wave on each side. Why a half wavelength? Well, it works out really nice because the voltage and current distribution makes this a very happy antenna. Think about this. I have a conductor. I'm ramming current into it in the middle. That's my job, right? Current, got to deliver current to the antenna. I've got high current right here, high current. How much current can there be flowing at the end of a conductor? You know, it just connected nothing out here. Well, out there can't be very much current. It pretty well has to be zero. So that's what we call a boundary condition. So I must have zero current nearly at both ends. So I have high current in the middle, low at the ends. In fact, the distribution is roughly the shape of a sine wave as such for the current. And meanwhile, the voltage does the opposite. Remember, like constant power, voltage times current is kind of constant. So the voltage out here is very high. In fact, on a typical dipole, it can be thousands of volts even. So the voltage does the opposite. Voltage is very high, low in the middle, high at the other end. And that's when the antenna is what we call at resonance. So it's at the magic frequency where this is the exact half wavelength long. So that's the most fundamental, simplest dipole there is. You can figure out what the length of this thing is. Remember the old wavelength is 300 divided by megahertz, something like that. It ends up being a little shorter than that because once again, we're dealing with it's going a little slower than the speed of light. So you have to look at the formulas. It'll end up a little bit shorter than you expect. So there's the most basic dipole. Now, one of the things I mentioned about this was this thing about feeding with coax, which is what we all do, of course. And we had, remember the old skin effect thing, and here we are. So I have the center conductor going, and I have the shield going over here, and that's fine. But remember that thing about the outside of the shield is also connected to this side. So this antenna actually has a mysterious third element that I don't have real good control over. How long is this coax? How does it compare with the length of this quarter wavelength element over here? I don't know. Is it magically happen to be a quarter wavelength? There's something else? I don't know. What's its impedance look like when it finally arrives here? I don't know. Well, that extra piece right there can then effectively distort the pattern that this antenna produces. So what we do is we add a balun. Stick that on here. There's my trusty balun. That's a symbol for it. It's known as a common mode transformer. So I've added this balanced, unbalanced here, and its job is to stop this current from ever arriving on the shield of the coax. I've now effectively disconnected the shield of the coax on the outside from this element of the antenna. It also prevents currents that are induced on the shield, say from noise. I come along with some noisy thing, maybe it's down in my shack, I don't know. And I've injected noise onto the outside of the coax, not on the inside, it's shielded. It doesn't get through the shield, it just rides on the shield. Well, that noise current comes up and stopped cold by this balun choke right there. So once again, I would build an antenna with one of these at the feed point, something like that. And then I wouldn't have to worry about that little problem. So we have a balun there. So there's a lot of things you can do with a dipole. First thing, let's talk about the pattern that it produces. All right. So I've injected current in here. The current's flowing in these conductors. It generates an electric field that's oriented along these elements. That's the electric field. And we have this old thing we call the right-hand rule for magnetism. If I have current flowing the direction of my thumb, the magnetic field is in the direction of the curl of my fingers. The current going plus to minus, and the magnetic field goes north to south. So the magnetic field is around these conductors. So the magnetic field is this way, and they're always perpendicular. So when this launches my energy off into space, disturbing the eternal universe, the electric field is horizontal and the magnetic field is vertical. Because of the structure of this antenna, this antenna has what we call a pattern. So what's the pattern of an antenna? Well, when I had my little balloon, it was just this kind of point in space, you might say. And you can imagine if I did something silly with my balloon, like I hooked it up to the world's fastest little air pump, and I made the little balloon pulse or something like that. Effectively, it would be radiating symmetrically in all directions, up, down, sideways, every direction. But we call that an isotropic radiator. So an isotropic radiator, you can't really build one. You really have to have a wire hooked up to it, and that screws it up. But an isotropic radiator is kind of a physical reference that everybody uses. So when we talk about an antenna having gain, what's your gain? Where's this gain coming from? And I'm putting power into it. I'm not creating more power. What am I doing? Well, I'm thinking about it as focusing the power. Okay, it's the pattern of the antenna compared to isotropic. The isotropic radiating in every direction. Well, this dipole has a little bit of gain, and actually up in free space, it's 2.2 dB. So that's an enhancement of about a factor of 1.6. Now, how does it get that pattern? Well, this antenna has a pattern that looks like it radiates equally in all directions, up, down, forward, back, this way. It doesn't radiate at all off the ends. So that's what I've done. I've taken, instead of radiating sideways in this antenna, all the energy is going broadside, up, down, that kind of thing. So I've improved my gain by a couple of dB simply by building a simple dipole like this. There's an additional enhancement in the real world because of the ground. It turns out that horizontally polarized energy like this actually reflects off the earth. So when I mount this up at a decent height, wavelength or something, get up fairly high, that energy reflects off the earth. That's the energy that otherwise it's kind of going into the ground. The energy going into the ground isn't tremendously helpful, although some of it does reflect upward as well. What I really want is stuff that's kind of headed off to the horizon, kind of going up in the sky. Well, that's what happens. A lot of the energy bounces off the ground, heads on up, and adds to the direct radiation. And that enhancement is on the order of about 5 dB, 5.5. That's almost getting close to a factor of 4 increase in effective power going that away, or that away too. So horizontally polarized antennas have that advantage. Vertically polarized antennas do not. So here we have a simple dipole. It has a little bit of gain. It's very, very easy to understand. You make it half wavelength long. You tune it up by adjusting your length a little bit here. And when you're building one out of wire, you can do that by, cut it long, as we say, cut it longer than you think it needs to be, and you just fold the wire back on itself and wrap it around. That's just fine. Simple way to tune it. We always end up go, oh, I'm going to cut the wire off, and then you always cut too much off, So just fold it back on itself. So that's trimming a dipole. Great exercise. It's got to be part of the ham radio experience is trimming dipoles, right? So the other thing about dipole is well, what's its impedance? Okay, well, I want a 50 ohm antenna. I got to have that perfect SWR, or it's no good. Oh no, that's not true. Well, what is the impedance of the dipole at the feed point? And some people say, oh, it's 72 ohms. Well, it's 72 ohms if the thing is, say, 1,000 feet up or something like that. If it's very, very far from the ground, say it's up in free space, this is indeed around 72 ohms for a properly resonant dipole. However, more often we're closer to the ground, and there is some coupling to the ground. The ground is conductive. It's lossy. It's kind of a nasty thing for radio frequencies, but it is what it is. So the antenna starts to interact with the ground. It's also reflecting off the ground. It's capacitively and inductively coupling the ground. So the ground matters. So what you find out is if you take a dipole and you vary its height, when you get very close to the ground, the impedance can get quite low. It can be 5, 10 ohms, 15 ohms, who knows? It depends on the quality of the ground. You just never know. It can be fairly low. Then as you move upward, the impedance will rise. It'll come back down again. It'll rise, come back down again. And eventually, if you get way up there, it resolves at 72 ohms. So, if you want it optimally bad, you put it at about 0.45 wavelengths. 0.4 wavelengths? Yeah, it's around 0.4 wavelengths. It works out to be about 100 ohms, just the way it is. And then you come down a little bit, down, 70. Oh, there, I got it just right. It's 50 ohms. It'll be 50 ohms somewhere at some altitude. So yeah, you never know really what impedance you're going to get on a dipole until you install it. But it will be in a very reasonable range. The SWR, I guarantee, once this thing is tuned, it's going to be less than 2 to 1. Don't worry about it. It's just fine. If you're lucky, it'll be closer to 1 to 1. Don't worry about it. SWR is not your mortal enemy. It does not tell you anything about the efficiency of the antenna. The antenna is always the same. It's just has a slight mismatch, and your antenna tuner will make up for that. So don't worry about it. And then as you change the length of the antenna, of course, you move away from resonance. That's where the current is perfectly zero at each end. The voltage is exactly optimized. As you change the length of the antenna, it'll be a less happy antenna, you might say. So that impedance at the center will start to be not a pure resistance. That's the thing about resonance. Resonance is a condition where inductance and capacitance cancel one another. They have opposite signs in phase. They cancel one another, and all that's left is resistance. Resistance is the place we can dissipate power. Our job is to dissipate power, turn the power into distorting that electromagnetic field. So the resistive part is what we really want. So if this antenna is mistuned, what we start to find is that at the feed point here, it'll start to become either a bit inductive or a bit capacitive, which is, again, not the end of the world. It just means it will affect your SWR as your antenna is slightly mistuned. Not a big deal. It's just something to be aware of. Now, if you use an antenna analyzer connected to your coax, your antenna analyzer can read that out directly. It'll read out resistance and reactance, R and X are the values. You read them out directly. And you can use that if you want to do very sophisticated things like build complex matching networks and things like that. But for the rest of us, don't worry about it too much. Your antenna tuner will take care of that extra inductance or capacitance to happen to show up there. Efficiency. All right. So if this thing is just made out of copper or aluminum, something like that, the efficiency should be very, very good. Very, very little loss in the materials. If I make it out of steel, like these things are, I'm going to give up a little bit of efficiency. It's hard to say exactly what the simulation programs you can actually put the kind of metal in there, and it will tell you. It's not a horrible loss, but it turns out you can actually use it to your advantage to have a slightly lossy conductor. One thing that happens is on certain bands, resonance literally occurs at one frequency, but I want to operate on many frequencies over, on a given band, like 80 meters is 3.5 to 4 megahertz. That's a pretty wide bandwidth. I mean, there's a lot of change in frequency there, and I can tune this up somewhere, but it's not, the match won't be quite as good and things like that. Oh, okay. Well, one of the ways that you can improve the bandwidth of an antenna is by resistively loading it. And actually, there are antennas designed for what we call ultra-wide band communications up in the microwave range. And what they do intentionally is they make the conductors out of a resistive material. In fact, Ron and I worked on an antenna where it was fabricated on a circuit board of all things. They do that a lot in microwaves. You have the antenna it's a circuit board. It's got wires on it, right? Make a dipole. And they actually soldered resistors, not resistors, a whole bunch of them, low value, resistor, a whole bunch of resistors. And what that did is you start kind of damping out this inductance and capacitance that you'd otherwise see. And the match, the SWR, tends to be much better over a much broader bandwidth, with the trade-off of additional loss. So once again, you've traded efficiency for a better match. You've kept the transmitter happy. And this is a case where they couldn't use the trans match. And worse than that, they had to cover a very wide bandwidth. It was the trans match, antenna tuner only works at one frequency. So how do I match a whole bunch of frequencies at once? Well, you can't. So you do this resistive loading on the antenna to broaden its bandwidth. Another way to do it is make the conductors fat. Sometimes you'll see a TV antenna that looks like a bow tie. Ever seen one of those things? Look at a bow tie, so you think that's what that's doing. It's actually making the conductor very fat. It also has properties where, as the frequency changes, like higher frequencies kind of stop as the antenna gets wider. It has really weird properties. Another thing to do is they make what's called a cage dipole. There's a famous picture at WNAW, the headquarters station in Newington, Connecticut. On 80 meters, they have a cage dipole. And what it is they have 4 conductors that come off each side, and they're spread apart, big spreaders. They're like 2 or 3 feet apart. It's a big cage. And when you have a very large diameter conductor, you also get a wider bandwidth with no loss, no extra loss either. So that's a really cool way to do it, but it's more complicated. You need more wires, and it's bigger and bulkier and harder to build, stuff like that. But that's another way. So when you see an antenna like that, why is it using such fat conductors? Well, that's actually increasing bandwidth, as it turns out. It's kind of neat. So, all right, so that's your basic dipole. And I claim that if you can understand those basic features of this dipole, you probably can, in your head, analyze most antennas that you see, because every antenna will have, there will be 2 sides to it, cold, plus and minus, whatever you want to call them. There will be 2 sides to every antenna. You just have to find them. Sometimes they're hidden. Sometimes someone forgets to include the other side. But nevertheless, there will be 2 sides. And it's just a matter of how they're oriented and configured and what they're made of. But otherwise, it's all the same. So what else can I do with this? Well, the first thing that happens is, well, I want to build this dipole and I haven't got room. Okay, my yard's too small, 80 meters, needs to be 132 feet long. I haven't got 132 feet. What should I do? Well, there's a bunch of things you can do. First thing you can do is you can start bending it. So I have another little gizmatras here.
Okay.
Question?
Yes.
It would probably be a good idea to mention, which you're probably going to do anyhow, that both sides of the antenna need to be adjusted the same exact amount, not just adjust one side and let the other one go.
That's right. Yeah, if you have a dipole, if you want to keep it symmetrical, if you cut something off one end, you want to cut the same off the other end to maintain the balance. We call it a balanced antenna. It's a very, very happy balanced antenna. So I'm stuck in a yard, I got no space. Well, the beauty of a dipole is it's still going to work even if it's bent. So I came to the corner of my yard and, well, I had to bend it. It's okay, folks. It's okay. Pardon? Clancy's antennas are all bent like that. Yeah. Yeah, I had the same problem. So, you end up going whatever direction you have to go. It may have to turn corners, it can be bent up and down. It gets to the corner of your yard, it goes down the fence line a little ways, it goes down. You have to insulate it. It's high voltage out at the end. You have to keep it insulated. And you make sure that nobody can touch it if you're operating, because it's very dangerous. But yeah, you're free to bend it. It doesn't have to be a straight antenna. It can go around, it can be bent and things like that. So what? The pattern's not perfect. Well, the pattern's never perfect. The pattern's only perfect when it's up in free space. Maybe it's too low. Better to have a too low antenna than no antenna. You need something up there, so don't worry about it. So yeah, so you're free to bend and mangle a dipole any way that's necessary to make it fit. There's other ways to shorten dipole, or any antenna for that matter. Question?
Yeah.
Okay, so the question is the advantage of using coax versus ladder line to feed any antenna. The ladder line in principle has slightly lower loss for most circumstances, a reasonable length. You're going 100 feet or something like that. It's of no concern whatsoever. Ladder line is generally a pain to work with. It's harder to feed through your house and things like that. And it absolutely requires a transformer at the end, at the transmitter end, in order to match its weird 450 ohms or whatever shows up to the transmitter. So ladder line is a classic, and it actually, the ladder line, because because of its open wire nature, it normally ends up becoming part of the antenna. The ladder line itself is an element of the antenna. So you may have a dipole with ladder line coming off it. Well, that entire ladder line is part of the antenna. There's no balun, there's no choke, there's nothing like that. It's part of the antenna. So depending on the frequency it's at, you may be presented with high current in different spots, high voltage, and that's where we have problems with RF in the shack. That's the classic problem. You key the mic and you get burned on your nose or something like that, or all your USB devices disconnect. That's RF in the shack, and that's classic with open wire line like that. So there are certain issues you have to deal with. But with careful design, ladder line can make a very effective antenna. It has for 100 years. So we want to shorten our antenna. Okay, there are a couple other ways we can shorten a wire antenna or any other antenna. The first is we can use an inductor. So basically, you just take your wire and you wind it up. In fact, there's antennas like a ham stick, and it's just a helix. It's just a fiberglass rod with a wire wound around it. So you can take your 60 feet of wire and wind it around, I don't know, a 30-foot length or something like that, and shorten it significantly. Or you can use, we'll call it more of an inductor, a loading inductor, as we call it, and place that somewhere along the antenna, usually kind of close to the feed point. And so literally all you've done is wind up part of the antenna and kind of make it disappear into this more compact structure. Another way to do it is we call a capacitance hat, and you'll see all kinds of capacitance hats. In this case, I have a little T up here on this wire. A capacitance hat is way out at the end of the wire. There's not much current up here. Okay, we're out at the end, not much current. A dipole, in most antennas, the real radiation is where the current is, and the current is at the feed point. Out at the far end, there's not much current. The field is not so intense out there. So anything you do with an antenna, your job is to get the feed point up as high as you can, get as long as you can, things like that. Focus on the part of the antenna that's near the feed point. That's the business of an antenna. So a capacitance hat is simply a tune, as you call it, is simply a tuning device. So this is, once again, you take your dipole and you bend and mangle it as you need to do to make the thing tune. You can have more than one conductor out at the end. There's all kinds of different antenna designs for VHF and other things that have these funny little things, sticking out at the top, and especially on the low bands. You're trying to build an antenna for 160 meters. Good heavens. These are enormous antennas. No one has space for those things. Actually, a guy on this call, Ken N6RO, does have space for 160-meter antennas up at his superstation in Oakley. But that's one of the few places you'll find that has that kind of room. So instead, we end up using things like inductors and these capacitance hats to shorten the antenna. The capacitance hat is extremely efficient. There's no added loss from a capacitance hat. It's very good. You can run into loss problems with inductors, with loading inductors. And the worst thing to do is to have the loading inductor right at the feed point. So, we talk about, we want lots of current in the antenna, and the current is where the field is being radiated from. That's the business part of the antenna. Well, if this inductor is right at the feed point, basically I've compacted the antenna a bit. And another problem occurs is that the high current is flowing in this inductor, and depending on how I make this inductor, it could start to dissipate some power. We see that in certain kind of trapped antennas, things like that. If you don't build the inductor sufficiently robustly, like using large conductors and things like that, an inductor can become lossy, and you'll see it especially if you run high power. A good compromise is to put the inductor, say, halfway up the antenna, and you'll see like even little antennas on car roofs, little wiry vertical, and it has a little inductor right in the middle of it. That's a really good place to put it. That's guaranteed not to impact the efficiency too much. So that's a couple ways to shorten any wire antenna. Wind it up over its whole length, if you like, loading inductor, capacitance hat, along with bending and folding and things like that. All those tricks are usable. Sometimes you need them all in order to fit into a smaller space. The next thing that comes up is where you want to run multiple bands. Everybody, we got lots of bands, lots of hand bands, and I say this is good for basically one band, one frequency. That's kind of limiting, Well, there's lots of answers to that. So here's one. Let me add a couple elements. There we go. Okay, so what do I have here? These are parallel dipoles. And we start to call this a fan dipole. And in principle, there's no limit to the number of additional elements I can add on here. This is what I have at home, it's fan dipole. So I have my longest wavelength here and a shorter wavelength hanging under it. Typically, these would be wires, and I'm gonna put little pieces of plexiglass or maybe PVC pipe or something like that to keep them separated a little bit. And because of the nature of any element like this is that when it's at resonance where you're trying to use it, the impedance here is very low, and the current goes where the impedance is low. So that's great. So if I'm on this frequency, this element has low impedance, and the current will indeed flow here. Whereas this element is too short, current won't flow here. Now they do interact a little bit. It does make a little difference. This thing looks like a little inductance. It looks like a little capacitance. It looks like something at the feed point. So they do interact a bit. And the tuning can take a little extra time because you change one, it changes all the other bands. But there's some procedures you can go through. So the good news is this is still your basic dipole. It just happens that there's several of them in parallel. So a fan dipole, again, it may cover 3, 4 bands, something like that. It's a very, very good antenna. Highly recommended for backyard antennas, the fan dipole, because it's very simple. Again, easy to understand, relatively easy to tune, easy to build. It's a balanced antenna. It's a happy antenna. Little balun in the middle, that kind of stuff. Either coax. Yeah, this is good. Something like Alpha Delta, they make one as a kit ready to go. The ham club at the lab has one hanging up over the shack there. Yeah. Did until it fell down, right? Oh, you moved. Well, okay. But Yeah, so the fan dipole is a very, very good choice.
Putting them at right angles.
Yeah, right angles. So yeah, and there as well, there's nothing saying that these can't point in different directions. You know, these elements can be pointing off, they can be perpendicular to one another. They can go, well, I got a tree over here and I got a pole over there and a house over there, whatever, it doesn't matter. They can go any old direction you want. That's fine. And they just come back to the common feed point. So that way you only have one piece of coax and it feeds multiple bands. Pretty cool. There's another interesting thing happens is the dipole is also roughly resonant at its third harmonic. What the heck is a third harmonic? Multiply the frequency by 3. So how does that work out? You have to look at, okay, at the fundamental, at the voltage, let's say the current goes like this. At the third harmonic, it makes a couple cycles, makes 3 cycles. 1, there's a peak, there's a peak. So at the third harmonic, this thing will also be resonant. And the classic use for that is 7 and 21 megahertz. So that's 40 meters and 15 meters. So you kind of get a 2-for-1 sale. The antenna will tune up. You kind of build it for 40. It will also work on 15 meters. It's not perfect, but it's pretty close. So you do get kind of a 2-for-1 sale on it there. That's not a bad way to go. There's other ways to do that, to get multiple bands. There's another thing called a trap. So I actually have a little simple trap here. So what is a trap? A trap is a little, in this case, parallel resonant circuit. So what I have here, a little hard to see on the camera, it's an inductor, and inside it I have a big capacitor. We call it a doorknob capacitor. It has to be rated for high voltage, fairly high current. So what is that? A parallel resonant circuit at resonance looks like a high impedance. So think of it as a switch. When you hit its magic frequency, this looks like an open circuit. So if I place one of these in each side of my dipole at some strategic location, when I get to that frequency, I've just disconnected the end of my dipole. So my dipole is now much shorter length, right? So at a low frequency, this just looks like a loading coil, which actually helps make my long antenna a little bit shorter. It's a little bit of a loading coil. That's not a bad thing. At a really high frequency, the capacitor shorts this out. So at a really high frequency, it just shoots on past. So what typically for a trap dipole, or you've probably seen trapped Yagis, the classic high gain, TH3 or the Mosley TA33 and things like that. And they have traps in the elements, and that's what they are. Think of these as switches. Okay, so you get to a frequency and it chops off the antenna at the desired places. The challenge with traps, of course, is getting tuned properly. And also, once in a while, you run into power handling problems. Again, I mentioned the loss in inductors, the high voltage across the capacitor. It tends to be kind of under stress. So there's a lot of ways to build traps. They do them with coax and wound up. There's all kinds of different ways to make traps. Some are very clever. They have to be used with care. You have to watch the power level and things like that. It's not unusual to have a flaming trap. There's lots of high gain antennas with aluminum dripping off of them and things like that. So that does happen. They get contamination, things like that. So traps can be challenging sometimes, but it does let you can buy a ready to go trap dipole for 3 or 4 bands or something like that. Trap, whatever it takes, and it kind of looks like one wire. And that's all you have to deploy, and it's ready to go. Not, so that's a fair choice, for giving yourself multiple bands. Another way to do it is, okay, here I have a dipole for some band, and right nearby, I simply place another element. This is a half wavelength at some other, say, higher frequency. I just place it nearby. I just install it nearby. So what's going on here? What does that do? Well, it turns out this acts like a transformer. Remember, I have a magnetic field around my conductor I'm driving current into. And when the magnetic field, a changing magnetic field, wraps around another conductor, it induces a current in it. That's how a transformer works. Magnetic field coupling from one. So these sit here, and also there's capacitance between them, but it's primarily magnetic coupling. So this element gets excited by the current flowing in this element. Now this element isn't resonant. I'm at the wrong frequency for this one, but I'm at the right frequency for this one. So this one ends up soaking up all the power. And this works very effectively. And a lot of modern Yagi designs are done that way. They call it a step forward Yagi. And you'll see just a ton of elements on the thing. And most of them, like you look at them like, man, they're not connected to anything. Well, it turns out they're doing this trick. So there's various names. One's called an open sleeve. There's different names for it. But this is another way that instead of a fan dipole where you actually make the electrical connection to the extra elements, all you have to do is put the extra elements nearby, and it works just fine. It's a miracle. But that's again, it's like transformer coupling. So that's another way a multi-band antenna is made. So that's kind of the dipole. Now let's see what are other things we can do to this thing. What if another way to get another a chance of getting more bands, more kind of resonant frequencies? What if we feed this off center? So we had antenna. This is now it's asymmetrical, right? Asymmetrical. All right. Well, let's see. Now, is this a happy antenna? Well, it's not as happy as it was anyway. The current, gosh, I like the current to be the same in both sides and the voltage to be all symmetrical. I'm like, well, it isn't exactly anymore. But it turns out, if you get this at just the right length, and it turns out you build this to be about 130 feet long, and you put the feed point about 20% of the way along the length of the antenna, you fiddle with it long enough, it'll turn out it actually will have resonances in quite a few of the hand bands. They call it an OCF, off-center fed, some off-center fed dipole. Well, I was saying, true dipole is really a perfect symmetrical balanced antenna, but OCF dipole, I'm okay with that. So the OCF is another common design you'll see for sometimes for portable use, but also for home. Again, you just have only one wire up in the air. Now, the challenge with an OCF is that the impedance here is sort of all over the map, and you may not have a red hot match. And this problem of balance can be rather severe, and it's very taxing on the balun, as it turns out. So this is one where we're getting a very good choke in line is quite important because of this asymmetry. So it really kind of exacerbates the problem of the feed line becoming part of the antenna. But with an appropriate choke or balun here, it can be a pretty effective antenna. And once again, it's still just your basic wire antenna, and as long as you can get current into these elements, it's going to radiate. So that's an OCF. That's the keyword. How about this? Let's see. Here's the hot side. There it is. There's the hot side. There's the cold side. All right. So I have this connected to this center conductor of my coax, and I have nothing on the other side. What the heck is this? This is a half wavelength long. This is a half wavelength right there, half wavelength. Huh. This is called an N-fed half wave. Everyone goes, oh, I don't know how an N-fed half wave works. Well, mine doesn't work at all. Mine works great. I go, what the heck is going on? You read the reviews on EHAM, and they're hilarious. They're just all over the map. Like, what the heck is going on? This is as asymmetrical as you can possibly get. Now, what the heck is going on? Now, I told you that every antenna has two sides. Okay, so here's one side. And in fact, there's even a resonant, half wavelength, which is cool. Where's the other side? And I'm trying to find it. Well, the only other side could be, well, maybe the shield of the coax. So, here's the shield of the coax. It's right here. It doesn't really go to anything else. So apparently that's the other half of the antenna. And so what people will do, they'll actually build this just like this. And they'll wonder, like, God, I'm getting RF in the shack and all my USB devices blew up and what the heck is going on? Well, it's because there's no what we call counterpoise. There's no other half to the antenna. Where is it? Worse than that, what's the impedance here? Well, let's see. The high current is in the middle of this half wavelength. The high voltage at the end. So the impedance here is very high. Well, the first thing you have to do, if you have any prayer of getting this to work, is add one of these. You got a transformer. This is basically a step-up transformer. It steps up 50 ohms to something very high. A lot of times they're 80 to 1 and things like that. It's a very high impedance step up because this is high impedance right here. Okay, fine. Now I can kind of match 50 ohms to some high impedance in principle. That's good. Okay, I got that much. That's where you put the antenna tuner at the antenna, like we talked about. All right, so I got that. Okay, check. So I got my OCF. I've got my half wavelength. I have a matching transformer. So in principle, I can couple current into this thing. I'm driving at the end. That's okay. It's okay. I've got a match. I'm able to drive current into it so it'll radiate. But where's the other half of the antenna? And this is where all the OCF stuff goes off the rails and into the weeds and nobody knows what's going on. Well, the answer is there has to be a counterpoise. There has to be something somewhere. You can choose to make that the coax and you put a choke farther down the coax somewhere. Or you could choose to put even a relatively short sort of counterpoise at the other end. And now it's a little more like, kind of like the off-center fed antenna. There has to be, I think of it as a current return. It's like current flows in circuit, right? It goes out one place, comes back the other. That's how you think of it. Very logical. And it really does work that way. So you have this thing excited, but there has to be another connection to the other side of the coax. So what's missing on most of the OCF designs is explicitly addressing the need for what we call a counterpoise. So like here's Dave who goes up doing soda stuff, and he along with Roberto, and what do they use? They use an end-fed half-wave. They use it all the time. But what do they also use typically is a counterpoise. They'll have this extra little piece of wire on the other end, they throw it on the ground. That's the counterpoise. It has to be somewhere. So it can be the coax, and you put a choke somewhere to protect your station from all this current that gets induced on the coax. It has to be a choke someplace. But there has to be another half somewhere. So look at OCF designs and see what you see. See how they address it. They say, oh yes, and by the way, you must have a counterpoise. And if they say that, they're paying attention and they got it right. If they say, oh, no counterpoise needed, where did they do it? Did they use the coax? Did they choke down here? They did something. You have to do something. Nature will find a return. And that return, may be, farther down the coax and lighting up your station and blowing up your USB devices. So watch it with the OCFs. All right. Next, let's have some fun with other kinds of antennas. So what else can we do with our little gadget I have here? Always have our balun. Don't leave home without the balun. Got to have that choke right at the feed point. All right. So what else can we do? How about we do this? Ha! I now have a vertical. Now I've gone to vertical polarization. I'm driving this element right here. It's vertically polarized. So the electric field is this way, my magnetic field is that way. What are the properties of vertical antenna? Well, the vertical element typically is a quarter wavelength long. And again, where is the other side? Oh, here it is. It's over here. Here's the other side of my antenna. And this can, on a vertical, typically it's either called a counterpoise or it's called a radial. A radial is a very common name for it. There could be more than one radial, very commonly. We'll talk more about that. But the main thing is we have this vertical element, quarter wavelength long, still have our balun. It still matches roughly to 50 ohms. Vertical polarization. The nice thing about a vertical is it tends to have what we call a low radiation angle. Now, if you're doing DX, we are bouncing off the ionosphere, trying to go long, long distances. We tend to like a low angle of radiation, low takeoff angle. So it heads off, bounces off the ionosphere, bounces off the Earth. So the low angle radiation is very good, and you automatically get that with a vertical. Whereas the dipole, you'll only get that if you mount the dipole very, very high. If the dipole is near the ground, a lot of the radiation is straight up, which is good for short haul communications. You're trying to work, within the US or something like that. It's fine. Dipole can be very low, works okay. For DXing, there can be advantages to having a vertical. Now, one thing the vertical doesn't get is the gain enhancement from reflections off the ground. In fact, with a vertical, the ground is your mortal enemy because this vertically polarized radiation is directly absorbed by the Earth. It's a disaster. And this is very, very important to understand, verticals. So what can we do to prevent the Earth from soaking up the radiation on our vertical? Well, I have here a teeny tiny vertical that I can play with more easily. I checked it. It's resonant at 280 megahertz for what it's worth. Okay. So sometimes they would call this a ground plane antenna. Okay, you have and again, this is a quarter wavelength long radiator, and these are quarter wavelengths long elements here. If this is up in space, we call these elevated radials. Now, this can work at any frequency. Doesn't matter if they just get longer at low frequency. Elevated radials. You can have any number of them. You can have 1, 2, 10. Doesn't matter how many you have. It turns out kind of an optimum combination is around 3 or 4. It's good enough. But what's nice about this is you can mount this antenna anywhere you want, any height you want. Higher is better, by the way. You'll get a better lower radiation angle. And you're getting away from our lossy Earth. So once again, you can still analyze it like a dipole. It has 2 sides. It has this side, has this side. And the fact that there's multiples of these makes no difference. Makes no difference whatsoever. The current is actually divided among the 4, in this case, 4 elevated radials. Quite often, verticals are mounted on the ground. Now, that's true for very low frequencies. An AM broadcast station. What does an AM broadcast station do? You go look at the towers that are sitting off in the muck over there, near the San Mateo Bridge and stuff. They're actually driving a tower, great big tall tower, low frequency, or 500, 800 kilohertz, whatever it is. Tremendously tall, long tower. So the tower is the driven element in that case. It's typically, it may be a quarter wavelength, maybe something else, but anyway. Where's the radials? Well, they're not running off in the air across the field. They're not using elevated radials. They're using ground radials. So in that case, you've lowered this all the way down to the Earth. These are in contact with the Earth. In fact, they may be even slightly buried, and that's fine. And they have completely different behavior. When they're up in the air, these are resonant radials. In fact, you can tune the antenna by trimming the radials. And in fact, if you adjust the ratio of the length of the vertical to the radial, you can change the feed point impedance. You kind of walk it around a little bit. You want 40 ohms, 50 ohms, 60 ohms. You can actually change it by adjusting. You can slightly change the pattern of the antenna depending on the radials. If I only have one radial, just a simple L, it'll radiate somewhat more strongly in the direction of that radial. And this is another good portable antenna. It's very simple, have a vertical element and then just one radial. It's a few dB bias to one side. So that's why symmetrical radials are nice. But when I lower this down to the Earth, remember the Earth is very lossy. Resistance, think about resistance. So what happens is the radials are no longer resonant when they're on the ground. They only need to be long enough that all this, if you want to call it return current, all this counterpoise current is absorbed by the radials. If I don't have radials on the ground, I'm using the Earth as the return. Remember, there's always a return. There's always another second side to the antenna. If it's the Earth is crap as a conductor. It's not your friend. It's very, very lossy. So if I don't have enough radials, and typically you start big numbers, 32 radials, 128 radials, and sure enough, that's what you have at a big AM transmitter site. It's hundreds of radials, and they go way out there. Those guys out trenching radials go in every direction around those big towers. They're very serious about that to keep their losses low. So yeah, if you don't have enough, the losses get very high. A funny thing happened. This is another thing where hams love low SWR, right? Who doesn't like low SWR? Yes, we all love low SWR. Okay, so I built a vertical, and I planted this thing in the ground. There it is, and I put down, I stretched a couple radials out in the dirt, call it good. Check the SWR, and by golly, it's 1-to-1, baby. I got 50 ohms there. Is that good? Well, it's a good match. I agree, it's a good match. But it's completely false. It's not what you want. So if you modeled it, you can only really find out through simulation what's happening. If you modeled it, you'd find out that vertical, sitting on the ground, if it had a perfect, ground plane, stuff like that, its impedance would be much lower. It might be 15, 20 ohms, something like that. Well, that's a mismatch. I don't want a 15 ohm antenna. That's no good. No, but that 15 ohm antenna is very efficient because you have a sufficient number of radials on the ground. So what you need is an antenna tuner is what you need to match your 15 ohms to your 50 ohm feed line. So this guy who has a crappy set of radials is seeing a really good match. Why is he seeing a good match? What he's seeing is the resistance of the earth. Now, part of the current is flowing in the few radials he put down. That's okay. That's helpful. The rest of the current's flowing in the earth. The earth is what? It's a resistor. The loss in the earth is in series with the radiation resistance of the antenna. The radiation resistance is the thing you want. That's where you're, changing the E field and the B field. Well, you only got 15 ohms or something of radiation resistance, and the other 35 ohms is lost in the earth. You're just heating up the earth, So yeah, you got a perfect SWR and crappy efficiency. So that's one of the things that happens very often with ground-mounted verticals. So you ground mount them, it's handy because, well, it's just sitting on the ground. The antenna doesn't have to go up as high and all that stuff. But the penalty is you have to lay down a lot of radials.
Okay. How
Yeah.
can we diagnose that? If I see a perfect SWR, how do I know?
Yeah, the best. So how do you tell that you have a lot of ground loss? One of the first things to do is if you can, while you're building an antenna like that, you put down some modest number of radials. You put down 4, 6, 8, whatever it is, and you measure the SWR, measure the impedance. Use your antenna analyzer, measure the impedance put it right at the antenna. Measure the impedance right there. Then add some more radials. While you're building, add a few more radials. Did the impedance go down? That's what you want. You actually want it to go down. You keep adding radials. You can see the impedance go down and down and down. And it's kind of diminishing returns. You keep adding them. Well, it didn't go down much. Then you're probably there. The only other way to do it is basically through simulation, EZNEC or something like that. The simulator can tell you for the geometry that you have, nominally what that impedance should be based on different ground qualities, things like that. But typically, it's a lower impedance than you expect, and if you got a really good match, it's probably because of ground loss. Pardon?
Length of the radius.
So the length of the radials when they're ground mounted, they can be less than a quarter wavelength electrical. The ground light travels much slower in media like the ground. So whatever you compute for quarter wavelength in the air, it can be quite a bit shorter when it's on the ground. Look in the antenna book. It has a ton of information in optimizing radial systems. They're very complex. Lots and lots of empirical data on how many to use, how long should they be, and things like that. There's a lot of futzing around. They have very good guidelines. If you follow the guidelines in the antenna book, you will not be led astray. And if you build it that way, your antenna should be pretty efficient. That's the best thing to do. Another question?
Yeah, following up on this, if your radials if you're losing to the ground and you're using a trap vertical, will you see a much flatter SWR across the whole thing?
Okay, that's a good question. So I have a trap vertical. Got a vertical that has our little traps in it that are used to turn this into a multi-band antenna. That's very common. And it happens to be one that requires ground radials. The old DX commander, that's a good one, actually uses, it's like a fan dipole. It has multiple different lengths conductors, but it needs ground radials. So yeah, if you have extra loss in the ground, remember, anytime you add resistance on the antenna, guess what? It increases your sort of SWR bandwidth. So you'll see a much flatter SWR curve. So that could be another diagnostic on a vertical for testing, do I have high loss? If you have very, very low loss antenna, the SWR will come down to minimum and go back up really sharp in a narrower bandwidth. You have lots of loss, it'll be very broad. Hey, this thing's resonant on all bands. Well, yeah, you've got a resistor. That's why it's resonant on all bands. It's not resonant. It's just a resistor at that point. We've got a few more things to talk about. Next thing I want to mumble about here is phased arrays. So there's things we can do to get higher gain. I want higher gain. All right, we got a dipole. Someone said, a dipole has gain of 2.2 dB over isotropic. A vertical does 2. That's right, a couple of dB, and that's all you get. Whether it's one of these or one of these, it's a couple dB, and they radiate in all directions. Well, how about we put more of our energy in one direction? We want more pattern gain. Well, how do we do that? Well, you need more elements. You need more elements out there. Okay, one way to do it is, say we built 2 verticals with suitable ground planes. Have 2 verticals. I drive them both. I split my power half, maybe 50-50 between the 2. I put the verticals at some strategic distance apart, maybe a quarter wavelength apart or something like that. So what happens is, if you're off at you look at this off at a distance, you'll see that depending on which direction these are oriented, you'll see that the field from these antennas, it may add or subtract because they're separated, they're some distance apart. And so it becomes a phasing argument. So typically what we do is we drive the 2 with a phasing network in between. We can drive them in phase, we can drive them 90 degrees out of phase, we can drive them at some other funny angle, whatever we want. And again, this is the thing that requires simulation, because your brain can't, puzzle out, well, what's that going to do? Well, I don't know. I mean, intuitively, it's hard to understand. It has to be simulated. Or again, look in the antenna handbook, and they'll show you what different phased arrays do. So you drive these with a certain phase angle, but the power is split between the 2. And what you find is, in a pattern, this can become, if they're driven one way, it can just be omnidirectional, and with not much gain. But you can very easily drive them, so it becomes what we call like a cardioid pattern. So cardioid, that's like a heart. It has a little null in the back. So it radiates, typically it'll be this way. It'll radiate more strongly in one direction. And very quickly, you can end up with something like 6 dB a gain out of this thing, out of this combination of a couple of verticals. And up at N6RO, that's what I built. I built a pair of these on 40 meters, elevated radials, very carefully adjusted, and by golly, it gives you something like 6 dB of forward gain in one direction. And if you switch the phase, you have a phasing box with relays in it, you can switch it so it radiates that way, this way, that way, or omni. So it's switchable, which is pretty cool. The other neat thing we make out of phased arrays, of course, the Yagi antenna. So the Yagi actually starts as a dipole, like everything else. So I start on the Yagi. This is my driven element in the Yagi. Then I add additional elements that are also resonant or close to it, and I put them in front or back of the thing. And these are called parasitic elements. They're located some distance away. And a parasitic element, again, gets excited by the current in the driven element, picks and then re-radiates current. Now, okay, I've coupled current into this thing. It's now, since it has current in it, it too is radiating. That's why they call it parasitic. So I've coupled energy into it. It's re-radiating it with a phase difference, some kind of phase difference. So depending where it is and how long it it can act as like a reflector, as it turns out. So the simplest way to build a Yagi is you have a driven element and a reflector behind it. The reflector would actually be longer than the driven element in this case, it works out. And that gives you very nice forward gain. And it also gives you what we call front to back ratio. You get kind of a null off of the back. You can also have what are called directors, which are a little shorter, and you can have some number of directors that are placed out in front of it. So a lot of times you see a Yagi, it'll have 5, 6, 7 elements, whatever it may be. And all those are used to enhance the gain and directivity of the Yagi. Now, a simple 2-element gives you a gain of about, it's about 5 dB more than a dipole. So it still has the properties of a dipole, but with 5 dB more gain, which is pretty cool. Then as you start making the boom longer, that's the number one thing, you make a very long Yagi, and then you start adding more elements, that gain can go up and up. Something like an infinite length Yagi ends up being like 16 dB a gain or something up there, somewhere on there. Those Yagis, you have 3 elements or something like that. It'll be 7 dB over a dipole, something like that. So that's the basics of a Yagi antenna. But what's neat is, in the end, you look in the middle, it's a dipole, and again, you can understand it's a dipole, simple, balanced, our good old friend with a balun. Yes, it always has to have a balun. And then these are parasitic elements. Beyond that, we get into other, lots of weird antennas. I should mention things like loop antennas. There's different things you can do with, you can take a dipole and you can bend it around like this, and now it's a halo. It's a lot of 2 and 6 meter halo antennas. It's just a dipole that's been bent around like this. If these are connected together, I now have an honest to God loop. A common loop antenna is one wavelength long. And if you feed that, it's about 120, 130 ohms or something like that. You need a little matching transformer or something to match the coax. And one thing they do with the half wavelength loop is they put another one nearby, and it's a cubical quad. Remember a cubical quad? You don't see them so much anymore. Instead of a Yagi, which is just nice straight elements, you build a quad. And usually they build them, make this a square or diamond, whatever, it doesn't matter. But you have a couple of these loops. And again, one of them is a reflector driven element. You may have a director, and you can have 2, 3, 4 element quads, things like that. They're very challenging to build, and even more challenging to get on the dang tower. And then you have to keep the thing up there in the weather. So quads have kind of fallen out of favor, but now there's some quad enthusiasts out there. And when you see it up on the tower, like, how the heck did he get it up there? It's there. It's a miracle. Loops can also be used just on their own. And the property of a loop is that it's directional in the plane of the antenna this way. It has a null when you look through it. And you can, as long as you can hang it up pretty high, it works reasonably well. But it's a full wavelength of wire, a lot of wire up there. I use a loop antenna like this. This is a different kind of loop antenna. This is just a little wire. And it has a capacitor. This is a variable capacitor in series with it. So this is a series resonant loop right here. So what happens is this is an antenna that responds only to the magnetic field. Kind of neat. Most antennas respond to electric fields and magnetic fields kind of equally. This only looks at magnetic fields. And when it's at resonance, what happens is the magnetic field couples to it. There's a magnetic field, goes through the loop. It generates very high current in the loop. And because it's resonant, it's the little kid on the swing, a pendulum or whatever, it's resonant. Effectively, the antenna has a very, very sharp resonance. It's like it automatically has gain. This is a very, very sensitive antenna. The only trick is to couple the power off of this loop. And to do that, we use, well, in this case, it's yet another little loop that's connected to coax. So that's a direction finding antenna based on a loop. Now, this resonant loop thing is another thing. In fact, I know the club had a build of these some years ago. You can transmit on things like this. And typically you have to build it out of things like copper pipe. The problem is the current is very high. Remember our skin effect problem and all that? You know, I have a very, very thin layer of copper that's doing all the conducting. If you're transmitting high power, the current is very, very high. So as a result, you build this loop out of copper pipe. Sometimes they do it with coax. Shielded coax is, you know, almost good enough, but copper pipe's better. And then this capacitor sitting here has to handle, you know, very high currents and voltages. So these vacuum variable capacitors, things like that, kind of complicated. But it makes a very compact antenna, because one that works on, actually, you get to work on many bands, 80 meters, 160 meters on an antenna. It's only a few feet diameter. And it is directional. So it nulls this way and peaks up that way. The challenge is efficiency with loop antennas. It's always efficiency. The loss in the copper itself is the main culprit. Some loss in the capacitor normally is not the problem. They'll self-destruct, but the loss in the loop can be substantial. And it's not unusual for a loop antenna to have an efficiency like 3%. So, you know, 97% of your power goes as heat. You just heat up the copper. On higher frequency bands, it can be better than that, like, you know, 30% or something. It's generally not an efficient antenna, but it's very compact. So a lot of people use those portable.
Good for, is it the same as the magnetic?
Yeah, sometimes you call magnetic loop antennas. They're pretty good on receive though. See, on receiving, you don't need really high gain. We have preamps for receivers. So they have very good properties for avoiding low noise, avoiding noise pickup. In fact, you can use a loop like this to null out a particular local noise source, like my neighbor's plasma TV. I actually had a receive loop I used to null out the noise from the plasma TV. So they actually make fairly good receiving antennas. And a lot of stations use them, you know, in addition to their primary antenna. That works pretty good.
The polarization.
It depends where it's fed. On a standard like full wavelength loop, the polarization will depend on where it's fed. If it's fed at the bottom or the top, it's horizontal. This makes it vertically polarized. To feed it on the side, like that. These small loops, they're all over the place. Sometimes it's hard to even figure out what the polarization is. Yeah, you can mount it flat. If you mount it flat, the radiation, it tends to be, yeah, it couples very strongly to the earth. The losses go way up. And most of the time we don't like horizontal loops, but some people swear by them. It's like, you know, everything works. You'll end up with horizontal polarization. It's hard to mount them very high, but you'll still have a horizontal polarization, and the pattern will generally just resolve to that of a dipole. It can have gain. You can make dipoles that are really, really long, by the way. They can be multiple wavelengths long, and you actually get some gain out of it. It's not just 2 dB, it could be 3, 4, something, make them very, very long. You just have to adjust the length so you can match it. The last thing I just want to mention is this business of simulation. There's a very nice code written at Lawrence Livermore, thank you very much, called the Numerical Electromagnetics Code, NEC. And that has been released into public domain, and it's available kind of embedded in a number of commercially available products. The main one I use is called the EZNEC. And these are electromagnetic simulators, and you put in descriptions of wires. You put the wire, I have a wire here and I have a wire here, and they're connected this way, and you put a source, you know, your transmitter there, and it's a field solver, and you tell it to have earth, and you tell about the quality of the earth that's below it, how high is the antenna, and so forth, everything about the geometry, and it'll show you graphically. It'll show you the antenna's pattern, the polarization. You'll see vertical and horizontal. You'll see the feed point impedance. You'll see all that will come out of it. So the simulators are very cool, and they're free, actually. These NECs are freebie. 4 NECs, there's several. Anyway, the simulators are all very good. So with that, you know, we've kind of come full circle. There's lots of antennas out there, folks. I mean, there's J-poles, and there's so many different weird antenna designs. I said, if you can kind of understand the dipole, you'll probably be able to get through and sort of understand how the other ones work. But anyway, so for now, I think we'll QRT, and thank you very much.